The radar operator at the Soviet Air Defense Command Center outside Moscow stared at his screen on a cold morning in December 1977. His equipment represented the pinnacle of Soviet engineering, a network of more than 10,000 air surveillance radars providing virtually complete coverage at medium to high altitudes over the entire USSR and well beyond its borders. The system could detect and track aircraft flying at these altitudes at least 200 nautical miles from Soviet borders under optimum conditions. Every radar station, every intercept facility, every command post operated under a single coordinating doctrine that had been refined through decades of Cold War tension. The operators knew their screens. They knew the signatures of American bombers, reconnaissance aircraft, fighters. They had tracked U-2s before surface-to-air missiles brought them down. They had monitored SR-71 Blackbirds screaming across the stratosphere at Mach 3.2, untouchable but always visible. Soviet air defense commanders believed their system could see everything that flew. They were wrong. 12 time zones away in the high desert north of Las Vegas, an aircraft lifted off from Groom Lake that would render that confidence obsolete. The prototype designated Have Blue looked like nothing that had ever flown before. Its angular surfaces violated every principle of aerodynamic elegance. Lockheed test pilot Bill Park advanced the throttles on the twin General Electric J-85 engines borrowed from the Northrop T-38 trainer and felt the aircraft respond. The faceted airframe, composed entirely of flat two-dimensional surfaces joined at sharp angles, climbed into the Nevada sky. On radar screens positioned around the test range, the returns were almost non-existent. A 50-foot aircraft was producing a radar cross-section smaller than a large bird. The date was December 1, 1977. The Soviet radar operators in Moscow had no idea that the rules of aerial warfare had just changed forever. The transformation began not in an American laboratory but in Moscow itself. In 1962, Soviet physicist Petr Ufimtsev published a dense mathematical treatise titled Method of Edge Waves in the Physical Theory of Diffraction through Soviet Radio Publishing House in Moscow. The work presented equations for predicting how electromagnetic waves scattered when they struck two-dimensional and three-dimensional objects. Ufimtsev had developed high-frequency asymptotic theory that could calculate radar reflection from finite bodies of revolution. Disks, cylinders with flat bases, cones, paraboloids, spherical segments, and finite thin wires. The physical theory of diffraction, as it became known, represented a breakthrough in understanding electromagnetic behavior. Soviet military authorities reviewed the work and granted Ufimtsev permission to publish internationally. They concluded it had no significant military or economic value. It was pure mathematics, theoretical physics with no obvious application to weapons or defense. The decision would prove to be one of the most catastrophic intelligence failures in Soviet military history. In 1971, the United States Air Force Foreign Technology Division at Wright-Patterson Air Force Base in Ohio translated Ufimtsev's book into English. The translation, documented as Technical Report AD 730-3203, was filed with the Defense Technical Information Center in Alexandria, Virginia. The document sat in the open literature, available to anyone with access to defense research archives. Most engineers ignored it. The mathematics were dense, the applications unclear. But at Lockheed's Advanced Development Projects facility in Burbank, California, a facility known by its nickname Skunk Works, a mathematician named Denis Overholser read Ufimtsev's work with growing excitement. Overholser recognized immediately what the Soviet censors had missed. Ufimtsev had not merely created theoretical equations. He had developed the mathematical tools necessary for finite element analysis of radar reflection. An engineer could use these equations to predict exactly how radar waves would behave when they struck an aircraft's surface. More importantly, an engineer could design surfaces specifically to redirect radar energy away from its source. The implications were staggering. If you could predict radar reflection, you could minimize it. If you could minimize radar reflection, you could make an aircraft effectively invisible to radar. Overholser brought the work to his colleagues at Skunk Works. They understood they were holding a weapon. The context made stealth technology not merely desirable but essential. During the Vietnam War, increasingly sophisticated Soviet-made surface-to-air missiles had devastated American air operations. SA-2 guideline missiles, directed by Fan-Song radar systems, had downed heavy bombers and forced tactical aircraft to operate at lower altitudes, where they became vulnerable to anti-aircraft artillery. The 1973 Yom Kippur War demonstrated the lethality of Soviet air defense systems even more dramatically. Israeli Air Force losses to Egyptian and Syrian SAMs were so severe that a 1974 Defense Science Board assessment concluded that in any conflict in Central Europe, Warsaw Pact air defenses would likely prevent NATO airstrikes from reaching targets in Eastern Europe. American air superiority, a cornerstone of military doctrine since World War II, faced extinction. Soviet radar-guided missiles were creating an impenetrable shield. NATO needed a way through that shield. Stealth offered the only solution. The Defense Advanced Research Projects Agency issued Lockheed Skunk Works a contract in 1976 to build and test two prototype stealth strike fighters under the codename Have-Blue. The project was classified at the highest levels. Even the existence of stealth research remained hidden from Congress, allies, and most of the military establishment. Skunk Works engineers, led by program manager Alan Brown and chief designer Denys Overholser, faced an unprecedented challenge. They needed to apply Ufimtsev's theoretical mathematics to an actual flying machine. The solution they devised was radical. Instead of the smooth curves that characterized every aircraft since the Wright brothers, the Have-Blue design consisted entirely of flat panels arranged at precise angles. Every surface was calculated to reflect radar energy in a direction away from the transmitting radar. The nose, fuselage, wings, tail surfaces, even the cockpit canopy were faceted like a cut diamond. Engineers nicknamed the early design model the Hopeless Diamond because its appearance seemed to mock every principle of aerodynamics. But the radar cross-section calculations were undeniable. The faceted shape would scatter radar energy in all directions except back toward the source. Lockheed assembled the Have-Blue prototypes using existing components to reduce cost and accelerate the schedule. The jet engines came from T-38 trainers. The fly-by-wire flight control system was adapted from the F-16 Fighting Falcon. Landing gear came from the A-10 Thunderbolt. Environmental systems were borrowed from C-130 Hercules transports. By combining proven technology with revolutionary airframe design, Skunk Works built both demonstrator aircraft under budget at $35 million total and ahead of schedule. Undersecretary of Defense for Research and Engineering William Perry provided critical support, protecting the program from bureaucratic interference and ensuring adequate funding. The first Have-Blue aircraft flew on December 1, 1977. Test pilot Bill Park reported that the aircraft handled acceptably despite its bizarre configuration. Radar tracking stations around the test range reported something far more significant. The aircraft was nearly invisible. Both Have-Blue demonstrators eventually crashed during the test program. Such losses were expected in experimental aircraft pushing technological boundaries. But the data gathered before the crashes proved the concept beyond doubt. Radar cross-section measurements showed that the faceted design reduced detectability by orders of magnitude compared to conventional aircraft. A Have-Blue prototype measuring approximately 50 feet in length produced a radar signature comparable to a small bird. Traditional fighters like the F-4 Phantom or F-15 Eagle had radar cross-sections measured in square meters, making them visible to ground-based radars at ranges exceeding 100 miles. Have-Blue's radar cross-section measured approximately 0.001 square meters or less from certain aspects. The reduction in radar detectability translated directly to reduction in detection range. The radar equation demonstrates that detection range is proportional to the fourth root of the target's radar cross-section. A tenfold reduction in radar cross-section reduces detection range by approximately 44%. A thousandfold reduction in radar cross-section reduces detection range by approximately 84%. Soviet radars that could detect conventional aircraft at 200 nautical miles might detect a stealth aircraft only at 30 miles or less. At that range, a stealth aircraft could already be over its target. The success of Have-Blue convinced the Department of Defense to fund production of an operational stealth attack aircraft. The program received the code name Senior Trend. Lockheed began development of what would become the F-117 Nighthawk. The F-117 refined the stealth principles proven by Have-Blue into a combat-capable aircraft. Engineers expanded the size to accommodate a meaningful weapons payload and extended the range for strategic strike missions. The F-117 measured 65 feet in length with a wingspan of 43 feet. It could carry two laser-guided bombs weighing 2,000 pounds each in internal weapons bays. External weapons carriage was impossible because any protruding stores would compromise the carefully calculated radar cross-section. The aircraft used two General Electric F-404 turbofan engines, the same powerplants that equipped the F-A-18 Hornet. To minimize infrared signature, the exhaust was mixed with cool ambient air in flattened, narrow nozzles. The aircraft lacked afterburners and was restricted to subsonic speeds. Breaking the sound barrier would create a sonic boom that would announce its presence acoustically, negating the stealth advantage. The F-117's radar cross-section remained approximately 0.001 square meters, comparable to Have Blue. The first production F-117 was delivered in 1982. The aircraft achieved initial operating capability in October 1983. All F-117s were initially based at Tonopah Test Range Airport in Nevada, far from population centers where their existence might be observed. Pilots and ground crew operated under extreme security restrictions. Families were told the pilots flew A-7 Corsairs. Training missions occurred only at night. If civilians reported strange aircraft sightings, Air Force public affairs officers deflected inquiries. The security measures worked. The existence of the F-117 remained classified until November 1988, more than 5 years after the aircraft became operational. By that time, 59 F-117s had been delivered to the Air Force. Pilots had accumulated thousands of flight hours. Maintenance procedures had been refined, tactics had been developed, the aircraft was ready for combat. Soviet intelligence had detected hints of an American stealth program but lacked concrete information about capabilities or operational status. Soviet radar designers knew in theory that low observable aircraft were possible, but assumed such designs would sacrifice too much performance to be practical. They continued to believe their radar network could detect any significant threat. If you appreciate discovering Cold War secrets hidden for decades, consider subscribing for future declassified revelations as we continue exposing the technologies that shifted the balance of power. The test came in the early morning hours of January 17, 1991. Operation Desert Storm, the air campaign to liberate Kuwait from Iraqi occupation, began with waves of coalition aircraft striking Iraqi air defense and command facilities. Iraq possessed one of the most sophisticated air defense networks outside the Soviet Union itself. Soviet military advisors had designed and installed the system. More than 3,000 anti-aircraft artillery pieces, 16,000 surface-to-air missiles organized in batteries across the country, overlapping radar coverage, buried fiber-optic communication lines linking command centers to firing units, and redundant early warning radars formed an integrated air defense system that military analysts called the most formidable in the world. Baghdad, the capital, sat at the center of the most heavily defended airspace on Earth. Rings of SAM sites surrounded the city. SA-2, SA-3, SA-6, and SA-8 missile systems provided coverage at multiple altitudes. ZSU-23-4 self-propelled anti-aircraft guns supplemented the missiles. Optically aimed anti-aircraft cannon filled any remaining gaps. American mission planners understood that attacking Baghdad in daylight would produce catastrophic losses. Even night attacks would be costly. Every NATO air force had studied this problem for decades. How do you strike targets defended by Soviet-designed integrated air defenses? 42 F-117 Nighthawks deployed to Qami's Mushat Air Base in Saudi Arabia provided the answer. In the opening hours of Desert Storm, F-117 struck 31% of all strategic targets attacked on the first day despite representing only 2.5% of coalition aircraft in theater. The first night they attacked the most heavily defended targets in Iraq, the Air Defense Operations Center in Baghdad, telecommunications facilities, command bunkers, airfields, and surface-to-air missile sites. Iraqi radar operators at their stations saw nothing. No warning, no tracking data, no opportunity to launch missiles or direct interceptors. The bombs arrived without announcement. Precision-guided munitions directed by laser designators destroyed buildings, severed communications, and collapsed bunkers. Iraqi air defense forces found themselves paralyzed. Their radars searched empty sky while their facilities exploded. The psychological impact was immediate and devastating. Air defense crews who believed their equipment could protect them discovered they were blind. Initial American reports claimed that F-117s hit 80% of their targets. Later analysis reduced that figure to between 41 and 60%. The discrepancy reflected the difficulty of bomb damage assessment and the challenges of precision strike even with advanced technology. What remained undisputed was that the F-117 was the only coalition aircraft that mission planners dared risk over downtown Baghdad in the first days of the war. The Air Force's Desert Storm White Paper stated this explicitly. Baghdad's defenses were simply too dense for conventional aircraft to penetrate without unacceptable losses. Dozens of F-16s eventually attacked Baghdad targets, but only after the defense network had been suppressed, and only during night missions when infrared missiles and optically aimed guns were less effective. The F-117 went first, alone, into the most heavily defended airspace, because it was invisible to the radar-guided weapons that formed the backbone of Iraqi air defenses. Over the 43 days of Desert Storm, F-117s flew more than 1,200 sorties and dropped more than 2,000 laser-guided bombs. Not one F-117 was hit by enemy fire, not one was lost to combat. The stealth aircraft proved essentially invulnerable to Soviet-designed air defense systems. While the F-117 demonstrated stealth in tactical strike missions, an even more revolutionary aircraft was already operational. The Northrop B-2 Spirit strategic bomber took the principles of radar evasion to their ultimate expression. Where the F-117 used faceted surfaces to deflect radar energy, the B-2 employed a flying wing configuration that eliminated vertical surfaces entirely. The aircraft measured 172 feet from wingtip to wingtip, but produced a radar cross-section estimated at 0.1 to 0.05 square meters from most aspects, with some estimates suggesting frontal radar cross-section as low as 0.0001 square meters. The B-2's size made this achievement even more remarkable. Conventional bombers of similar size, like the B-52 Stratofortress with its large fuselage and vertical stabilizer, had radar cross-sections measured in tens of square meters. The B-2's radar signature was smaller than a seagull's despite weighing 170,000 pounds fully loaded. Northrop engineers achieved this performance through multiple complementary techniques. The flying wing design eliminated the fuselage, vertical stabilizers, and other protruding surfaces that create strong radar returns. Every edge was carefully shaped to direct radar energy away from the transmitter. The skin consisted primarily of non-conductive carbon graphite composite mixed with titanium. Radar-absorbent materials coated the most reflective areas, engine intakes, control surface edges, and wing leading edges. An elastomer coating smoothed seams, screws, and joints that might create radar reflections. Engine exhausts were buried in the upper surface of the wing and cooled with ambient air to reduce infrared signature. The B-2 employed a sophisticated threat detection system to identify enemy radars and adjust its flight path to maintain the lowest possible radar cross-section toward active threats. Like the F-117, the B-2 carried all weapons internally to preserve its stealth characteristics. Northrop, like Lockheed, used Ufimtsev's Physical Theory of Diffraction as the mathematical foundation for its stealth design. But where Lockheed applied the theory to a relatively small tactical aircraft, Northrop programmed supercomputers to apply Ufimtsev's equations to the enormous complexity of a strategic bomber. Every square inch of the B-2 surface was calculated to minimize radar return. The computational challenge was immense. Engineers used early Cray supercomputers running for weeks to model radar cross-sections from every angle across multiple radar frequencies. The design process consumed years and billions of dollars. The first B-2 flew on July 17, 1989. The aircraft entered service with the 509th Bomb Wing at Whiteman Air Force Base, Missouri in December 1993. 21 B-2s were ultimately built at a program cost exceeding $40 billion. The per-aircraft cost approached $2 billion, making the B-2 the most expensive aircraft ever constructed. But the capability justified the cost. A B-2 could penetrate defended airspace that would require hundreds of conventional aircraft and extensive support operations to breach. Soviet and later Russian military analysts eventually obtained enough information to understand what had happened. They had provided the theoretical foundation for American stealth technology and failed to recognize its value. Ufimtsev's work, dismissed as abstract mathematics with no military application, had enabled the most significant advance in military aviation since the jet engine. Soviet air defense developers had focused on building more powerful radars with longer detection ranges, more sophisticated signal processing, and better integration between sensors and weapons. They had assumed that improvements in radar technology would always outpace improvements in low observable design. This assumption was wrong. The mathematics of radar detection meant that even modest reductions in radar cross-section produced dramatic reductions in detection range. Soviet radars could increase power and sensitivity, but they could not overcome the fundamental physics of electromagnetic scattering. A target that reflected almost no radar energy could not be detected regardless of how much power the radar transmitted. The realization forced a comprehensive reevaluation of Soviet and Russian air defense strategy. If American stealth aircraft could penetrate at will, the entire Soviet defensive architecture became questionable. radar-guided SAM systems that had been the pride of Soviet air defense engineering were effectively useless against stealth targets. Billions of rubles invested in integrated air defense networks could be bypassed by a few dozen low-observable aircraft. Soviet military planners began investigating countermeasures. Lower-frequency radars showed some potential for detecting stealth aircraft because larger wavelengths interacted differently with aircraft structures, but these radars sacrificed the precision needed to guide weapons. Bistatic and multistatic radar systems that used separated transmitters and receivers could potentially detect stealth aircraft by observing radar energy scattered in directions other than back toward the source, but such systems were complex and difficult to deploy. Infrared search and track systems could potentially detect the heat signature of stealth aircraft, but effective ranges were much shorter than radar detection ranges. Passive radar systems that detected aircraft by observing distortions in ambient electromagnetic radiation from television and radio transmitters showed promise but remained immature. None of these approaches offered a complete solution. By the mid-1990s, Russian military journals openly discussed the stealth threat. Articles in publications like Voyonnaya Missile, the journal of the Russian General Staff, acknowledged that American low-observable technology had fundamentally changed the aerospace balance of power. Some authors argued that Russia needed to develop its own stealth aircraft. Others contended that counter-stealth sensors offered a more cost-effective response. The debate revealed deep uncertainty about how to respond to a capability that had appeared suddenly and completely. The Soviet Union had collapsed by this time, and the Russian military budget had contracted severely. Developing a comprehensive response to stealth technology required resources that Russia no longer possessed. The admission was implicit but clear. American stealth aircraft had achieved a decisive advantage that Russia could not immediately counter. The operational impact of stealth extended far beyond the Gulf War. In 1999, during NATO air operations against Serbia, F-117s struck targets in Belgrade and throughout Serbia despite the presence of sophisticated air defense systems. Serbian forces eventually shot down one F-117 on March 27, 1999, using a combination of tactics that included careful observation of flight patterns, brief and precisely timed radar emissions to avoid detection by American radar-homing missiles, and a large volume of missile fire. The loss demonstrated that stealth aircraft were not completely invulnerable, particularly when operating in predictable patterns against a determined and adaptive adversary. But the loss also highlighted how difficult it was to shoot down a stealth aircraft. Serbian air defenses fired more than 800 surface-to-air missiles during the 78-day campaign and achieved only 2 confirmed kills, one F-117 and one F-16. Against conventional aircraft, such expenditure of missiles would have produced dozens or hundreds of kills. The stealth technology forced defenders to develop entirely new tactics and accept vastly reduced effectiveness. The B-2 demonstrated its capabilities in combat during Operation Allied Force in Serbia, Operation Enduring Freedom in Afghanistan, and Operation Iraqi Freedom. In the opening hours of Iraqi Freedom in March 2003, B-2s flying directly from Whiteman Air Force Base in Missouri struck leadership targets in Baghdad. The missions covered more than 15,000 miles and required multiple aerial refuelings, but the B-2s penetrated Iraqi airspace without being detected by air defense radars. Iraqi forces, equipped with many of the same Soviet-designed systems that failed to detect F-117s in 1991, remained blind to the attacking aircraft. The psychological effect was similar. Defenders discovered they were powerless against weapons they could not see. The B-2's ability to strike anywhere on Earth from bases in the continental United States created a strategic deterrent effect. Nations contemplating actions contrary to American interests had to consider that their most important targets could be destroyed without warning by aircraft their defenses could not engage. The development of fifth-generation fighters like the F-22 Raptor and F-35 Lightning II extended stealth technology to air superiority and multi-role missions. The F-22, which entered service in 2005, combined stealth characteristics with supersonic cruise capability and extreme maneuverability. Its radar cross-section was estimated at 0.0001 to 0.0005 square meters from frontal aspects, even smaller than the F-117. The F-22 could detect and engage enemy aircraft at ranges where it remained invisible to both enemy radars and enemy sensors. In training exercises against American and Allied air forces, F-22s routinely achieved kill ratios exceeding 20 to 1. Pilots of conventional fighters reported that they had no warning before F-22s appeared on their sensors at close range, by which time they were already within missile engagement envelopes. The F-22 created a new paradigm in air combat, one-sided engagements where the stealth fighters saw and killed opponents who never knew they were under attack. The F-35, designed as a more affordable multi-role stealth fighter, entered service with the U.S. Air Force, Navy, and Marine Corps beginning in 2015. Multiple allied nations, including the United Kingdom, Italy, Netherlands, Norway, Denmark, Australia, Israel, Japan, and South Korea purchased F-35s, making stealth technology widely available to American allies. The proliferation of stealth aircraft forced potential adversaries to acknowledge that any future conflict with the United States or its allies would involve attackers they could not reliably detect or engage. Russian and Chinese military planners invested heavily in counter-stealth technology, but the fundamental physics remained unchanged. Aircraft designed to minimize radar reflection would always have an enormous advantage over radars trying to detect them. The strategic implications of stealth technology extended beyond tactical military operations. During the Cold War, the Soviet Union relied on its massive integrated air defense network as a cornerstone of national security. The system was designed to detect and destroy American bombers before they could deliver nuclear weapons against Soviet cities and military facilities. Enormous resources were devoted to maintaining and improving this defensive shield. Stealth technology revealed that the shield had a hole. American bombers could penetrate Soviet airspace without being detected. The deterrent value of Soviet air defenses collapsed. If the defenses could not stop the attackers, they provided no protection. This realization influenced Soviet and later Russian strategic calculations. The balance of power had shifted. American first strike capability became more credible because Soviet defenses could no longer guarantee interception of incoming bombers. The shift increased instability because Soviet planners could not be confident that their retaliatory forces would survive an American first strike. Stealth technology, in combination with other American strategic advantages like precision navigation and advanced reconnaissance satellites, created a situation where Soviet military leaders understood they had fallen behind technologically and lacked the resources to catch up. The irony that Soviet physicist Petr Ufimtsev provided the mathematical foundation for American stealth technology was not lost on Russian commentators. Ufimtsev himself eventually moved to the United States, where he worked as a research professor at the University of California, Los Angeles. In interviews, he expressed no regret about publishing his theoretical work. Science, he maintained, should be openly shared. The failure was not his, but that of Soviet military analysts who failed to recognize the practical applications of his mathematics. Whether that interpretation was entirely sincere or represented a rationalization after the fact, the result was undeniable. Soviet authorities had reviewed Ufimtsev's work, failed to understand its implications, and allowed it to be published internationally. American engineers had recognized what the Soviets missed, applied the theory to practical design, and created a family of aircraft that rendered Soviet air defenses obsolete. The transfer of knowledge from Moscow to Burbank represented one of the most consequential intelligence failures in military history. The psychological dimension of stealth technology's impact deserves emphasis. Soviet and Soviet-trained air defense operators had developed their skills and confidence through decades of tracking aircraft on radar screens. They understood the signatures of different aircraft types. They knew how to distinguish bombers from fighters, how to track multiple targets simultaneously, how to direct missiles and interceptors. Their entire professional identity was built on their ability to see enemy aircraft and guide weapons to destroy them. Stealth technology invalidated that expertise overnight. The operators still sat at their stations, the radars still swept the sky, but when stealth aircraft were present, the screens remained empty, the operators were blind. The weapons they controlled were useless. This psychological shock extended beyond individual operators to entire military organizations. Air defense forces that had been considered elite units with critical national security responsibilities discovered that they could not perform their fundamental mission. The institutional confidence that had sustained Soviet air defense forces through the Cold War evaporated. Officers and analysts who had assured political leaders that Soviet air defenses could protect the motherland had to confront the reality that their assurances were worthless against American stealth aircraft. The broader message was equally disturbing for Soviet and Russian military planners. If American engineers could achieve such a decisive advantage in one domain, what other technological surprises might be waiting? Soviet intelligence had detected American stealth research, but the full capability had remained hidden until the F-117's existence was revealed. What other classified programs were underway? What other Soviet assumptions about the balance of power were wrong? The uncertainty created by stealth technology extended beyond air defense to every aspect of military competition. Soviet confidence in their ability to match American technology had been a central element of Cold War strategy. Stealth demonstrated that this confidence was misplaced. The American defense establishment could develop and field revolutionary capabilities in complete secrecy, while Soviet intelligence remained unaware or unable to respond. This realization had strategic implications that transcended any specific weapons system. The economic dimension compounded the military challenge. Developing stealth aircraft required enormous investments in research, advanced materials, precision manufacturing, and sophisticated testing. The United States could afford these investments. The Soviet Union and later Russia could not. The Soviet economy was already straining under the burden of military spending when American stealth aircraft became operational. Responding to the stealth challenge would require additional billions of rubles for research into counter-stealth sensors, development of Russian stealth aircraft, and modification of existing air defense systems. The money was not available. Soviet and later Russian military budgets could not support both maintenance of existing forces and development of new capabilities to counter American technological advantages. The gap widened steadily. By the 21st century, the United States had deployed hundreds of stealth aircraft across multiple types, while Russia had only prototype stealth aircraft and China was just beginning to field its first low-observable designs. The technology gap that stealth represented became emblematic of a broader American advantage in defense technology. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink. The story of stealth technology demonstrates a fundamental principle of modern warfare. Information dominance decides battles before the first shot is fired. Soviet air defense commanders believed they could see everything in the sky because their radars were powerful and their network was comprehensive. They were wrong because they measured the wrong variables. Detection depends not only on radar power but on what the radar is trying to see. An aircraft that reflects almost no energy cannot be detected regardless of how powerful the radar is. American engineers understood this principle and designed aircraft specifically to exploit it. They used mathematics developed by a Soviet physicist, applied with American engineering rigor and supported by American investment resources, to create weapons that Soviet defenses could not stop. The radar screens that had given Soviet operators confidence for decades became useless. The missiles that sat ready in their launchers never fired because their guidance radars never acquired targets. The interceptor aircraft scrambled to meet threats that were never detected. The entire architecture of Soviet air defense, built over decades at enormous cost, was bypassed by technology its designers never anticipated. Soviet military leaders thought they understood the game. They thought their radar could see everything. They learned too late that American engineers had changed the rules. The invisible aircraft that appeared over Baghdad in 1991 and Belgrade in 1999 were not the future of warfare. They were the present, and Soviet-designed defenses had no answer.